And we're back. Welcome back and happy Thursday. Today we'll be switching gears, pivoting to a different classifier generation method, namely decision trees. But in order to talk about decision trees for classifier induction, we need to talk about information theory a little bit. And so today we'll be talking about information and decision trees. But before we begin, some administrative bits. The reading for this particular module is at the following link from Princeton, and it's a very good read. It will also be on the course Blackboard site. So why don't we begin? So information, what exactly is information? When we mention that word, well, it conjures up many things. You think data, maybe you think features, but what is information really? Well, this picture is a picture of random noise. Noise has no structure, carries no information. Now, I don't know if you remember the days of tube televisions, but often when the networks for the air channels for the stations on the TV, when they went off the air after hours, there wasn't 24-hour TV even just up till 20 years ago, they would go off the air. And when they went off the air, there was just a random noise, no signal whatsoever through the airwaves. And if you tune to that channel, this is what you'd see. Now, let's compare that noise, no information, with the following. Now, they're very different from one another. One has structure, and that structure is not random. So there's a particular pattern for it, set of regularities. And so this set of regularities, the structure, is what we mean when we refer to the word information. So let's think about more closely what is information. Information is the dual of disorder. And so disorder has absolutely no structure. Things are changing, but there's no regularity that you can count on to how those things change. And so when you make a measurement, i.e. a random variable, some observation, the wider the selection of different values that you can take on, the more bits, the bigger the number of bits, or the more bits you need in describing all those values. So let's take a look at some observation. If an observation can take on n many values, well, in order to enumerate or count those values, you need enough bits to represent those numbers for the different values for 1, 2, 3, up to and including, say, n. So for example, if you have 65,000 values, you're going to need 32 bits to represent it if you can take on a lot of those values, because you need at least 16 bits to represent 65535. So if you have over 65535 many values, well, in 16 bits, you can represent 65,535. But if you have more than that, if n is like, say, 68,000, well, you're going to need more bits to represent that many values. And so this idea of enumerating all of the different values that your observation, and it's a stochastic observation, can take on, you're going to need a larger number of bits in order to represent them. And so let's say if you could take on 256 different values. Well, if you have 2 to the 8th power, that's 256, and you're going to need 256 or 8 bits of worth of representation to represent these enumerated observations, these 256 different values. And so this idea of whether you need a larger or smaller description relates directly to how much these observations can change, the representation of all of the different possibilities. And so this idea then, if you're going to describe what you can see for a stochastic observation, if something has no structure, i.e. it is random, it is noise, then there's a really large number of observations that you can see. If something has structure, it's not going to be an arbitrary set of values that you see. It's going to be a limited set of values. So if we go back to this picture, well, we see edges here that are light for one pixel and dark for the tree's pixel, and it doesn't change very much. Whereas here in the same location, well, you see light and dark and light and dark and light and dark. There's no structure to it. And so this idea of the descriptive length is what we talk about when we represent the particular observations that a variable can take on. And so you have higher disorder in a system because you have many more alternatives that a measurement can take on. And so here we have a uniform distribution. And as a roughly uniform distribution, you have, for the most part, equal representation of all the different values. If this is value 1, value 2, up to some large number of values, value n, if you have this uniform distribution over different values, there are going to be many more alternatives that it can take on. And that's going to be disorder, a lack of structure. But if we look at this other distribution, well, the values in this central region here, they're going to appear much more often than values away from the central region out on the tails, because the probability is higher for those central values. So what that means is that more often you're going to see certain observations, and it's only going to be very rare or relatively rare you're going to see other observations. This has structure. So there's lower disorder or more information because you have fewer alternatives represented for some particular observation or measurement feature or random variable. So let's look at information theory. Now, information theory was pioneered by Claude Shannon, and the original paper is still available, Mathematical Theory of Communication. It's quite an interesting thing to see. And Mr. Shannon worked for the phone company, for AT&T Bell Labs. And Bell Labs at the time was doing amazing research. And when Ma Bell or AT&T was broken up into the so-called baby bells, a lot of those groups kind of dispersed into various sub companies, or what now became the baby bells, and some of those baby bells are still around: Verizon, Pacific Bell, and so forth. But nonetheless, what he was after, he was working on problems in automated telephone switching and communication, and this was right at the precipice of the transition between analog communication and digital communication. And so in analog communication, you carried your signal over the electrical wiring as electrical impulses at different frequencies. You coded your signal. Now with digital, of course, you're representing your data or your voice signal and data as bits of information. And so one of the things that they were interested in is if you have different types of signals being transferred, like different frequencies of voice, how do you compactly transmit this information, those different values, frequencies for sound, across the wire? And so it was really, really key. And Mr. Shannon, Claude Shannon, initiated the field of information theory. And in essence, he was trying to measure the number of bits you need in order to communicate a signal. Because what is a signal? It's a bunch of different values. And so let's take a look at one of his major contributions, so-called Shannon Entropy. And in the literature, especially in the paper that I've linked, entropy, the Princeton paper, is called H, and this is the following expression. We have the negative sum of the log of the probability of a particular outcome of a measurement, random variable, times the probability. And so going back to our definition of what the expectation is, well, this is just the weighted sum of the log probability. And so you can think of Shannon entropy as the expected log probability, more correctly, the negative expected log probability. So here's our log probability. You're doing the weighted sum over all instantiations of the value xi. That's the negative expected log probability of random variable xi, for the ith outcome of some random variable x. So there's another piece of information you can measure. And in many cases, you have two signals. One signal is producing values at a rate of probability p of x, probability p, and another signal is producing values governed by probability distribution q, so q of x. is that rate of seeing a particular value for the other signal. Now, a so-called importance weight is the ratio between Q and P. So we write Q of xi over P of xi. Now, given these two probabilities, P and Q, and let's suppose this red curve, that's our P of x, and this green curve, that's our Q of x. And what we're measuring with this weight, this ratio, the importance weight as it's called, we're looking at the likelihood ratio expressing how probability P of x for one signal and Q of x, the other signal, agree on the probability mass over the support set x, defining all the different variable outcomes. And so they have the same support set, probability P and Q, but they have different proportions describing the occurrence of these different values. And so oftentimes one enterprise is to know how much do P and Q agree in how much probability mass they place on different parts of the support set over the domain X. So that's our importance weight. And so we can take our importance weight, and if we think about it, if Q over P is close to 1, that means both distributions P and Q agree on xi, value xi. And that means value xi is quote unquote important. Because if many different distributions agree on it, that means they place similar or the same or close to the same probability mass on value xi, and therefore that value must be important. If that importance weight is very small or very large, that means P and Q disagree. That means this xi, this value, is not so important, because if it were important, it would show up the same way for many different distributions. And so this importance weight is a way, the idea of agreement on a particular value between two distributions, P of x and Q of x. It's a way of talking about shared information that P of x and Q of x have. That means P of x and Q of x has something to do with areas of support where they agree, right? They're related. They must share information for those parts of the support set where they agree. So if that's the case, well, if we look at the overlap region between P of x and Q of x, well, the importance weight is going to be better for regions where they share information versus on the tails here, on the right of Q and on the left of P, they're not going to share much information. They're not going to agree very much. And so you can have the relative information between two signals. And in information theory, relative entropy, or Kullback-Leibler divergence, KL divergence, measures exactly that. And so we can take our importance weight, compute the log of the importance weight, that agreement between Q of x and P of x, and our KL divergence then between distribution P and distribution Q is just the sum. So we have a probability. We're going to take a probabilistic weighted average. The probability for each value xi, for all instantiations of xi, the log of the importance weight. So this is the entropy of probability Q, P, relative to probability Q, those two signals. And so if we think about this expression, this is the expected log odds ratio of P relative to Q. And so it says, on average, how much does P agree or differ from Q? And this KL divergence is a way of measuring the distance, if you will, or the discrepancy between two probability distributions. All right. And so we can also express this joint distribution. And let's say we have two random variables or signals that occur jointly. We have variable x and random variable y. So with these two signals, we call the joint entropy the following. So h of xy, again, this entropy framework, for all instantiations of x and y, we're going to take the weighted sum, but this time we're going to weight using the joint distribution for this random variable consisting of x and y, this joint vector. And so here we have log of P of xy. So this is nothing more than the average of the log joint distribution between these two signals governed by this joint probability P of xy. So we could say this differently, say the expected log joint probability between the random variables. All right. And so this joint entropy talks about the disorder or the number of bits to describe the number of outcomes, but this case, it's a joint occurrence, the outcomes for this joint occurrence, this random factor. And so we can also talk about the mutual information. This mutual information takes our signals and it says, okay, well, if they appear jointly, that means that there's some information coupling between them. And if there's information coupling between them, how do we measure the amount of the descriptiveness, the number of alternatives that we need for the number of bits to describe these alternatives? How much of it is due to their occurrence together versus their individual occurrences? And that's called mutual information. And so again, we have our double summation for all instantiations of value x for random variable big X and value y for random variable big Y. We're going to weight by our joint probability, p of x, y, and we're going to take the log of the following expression. Now here in the numerator, we have the joint distribution, p of x, y, and in the denominator, we have the product of the marginals, p of x times p of y. And when you have the product of the marginals, you're making an independence assumption. You're saying, what if x and y are independent? Now, they don't have to be independent in practice. They can share information. But you imagine if they were independent, we look at the ratio between the joint assumption, they share information, and the independence assumption, and express that as a log odds ratio. And so essentially what we do is saying, given the full coupling, and giving the independence assumption, we take the log odds ratio between the two, and we compute that probabilistic weighted average, weighting by the joint probability. And so this is the expected log odds ratio between the joint and the independence or the information coupling assumption. Coupling versus no coupling, we take those log odds ratio. How do they agree on the amount of probability mass? And this is kind of like an importance weight, if you will, between x and y, given the coupled version and given an assumption, a naive assumption that they were independent from one another. How much does the independence assumption and the coupled assumption agree on how they put probability mass or assign probability mass over the support set? In this case, it's a joint support set over x and y. And we call that mutual information I of x, y. All right. And so this mutual information, we rewrite that expression, we can express that in terms of the entropy. And so this mutual information then says the mutual information is equal to the sum of the individual entropies, so entropy of x plus entropy of y, and you're subtracting out the joint entropy between x and y. And so the mutual information is that part of the entropy that's not due to the joint coupling between x and y. It's what's left over. Okay. And so the KL divergence is not symmetric. And if you were to write the KL divergence and swap the parameters, KL divergence of P with Q is not the same as the KL divergence of Q with P. Of course, the left-hand parameter is always on the denominator, and the right-hand parameter is always in the numerator. So if we swap the first parameter with the second parameter, first parameter, second parameter for KL divergence, we get a different expression. Moreover, the first parameter is also going to govern which probability you're going to use to take the weighted sum for the expectation. So the KL divergence of Q on P is not the same as KL divergence of P on Q. We also have this thing called the Jensen-Shannon divergence. And what the Jensen-Shannon divergence does, it is a symmetric version of the KL divergence. It smooths out the KL divergence. And so it kind of tries to correct for that discrepancy where KL divergence is not symmetric. And so what the Jensen-Shannon divergence does, it takes the midpoint distribution. So it's the smooth average between P and Q, our two probability distributions corresponding to the two signals. And it says, okay, well, for half of the contribution for this measurement of difference, I'm going to take the KL divergence between the first probability and this midpoint distribution. And the second so it is symmetric because if you said Jensen-Shannon divergence of Q with P, that's going to be 1/2 KL divergence of Q on the midpoint plus 1/2 KL divergence of P on the midpoint. And so because addition is commutative, you get the same expression. So the Jensen-Shannon divergence is an extension of KL divergence intended to remedy this fact that KL divergence is not symmetric. And you can think of Jensen-Shannon divergence as a smooth version, smooth because we're taking the interpolated midpoint distribution. It's a smooth version of the KL divergence. Okay, and so some of the work that I did with my graduate student a couple years ago, we developed a new information theoretic measure. We call it the Shishini Jensen-Shannon divergence, or CJSD. Now, if we have the Jensen-Shannon divergence, this is what it looks like. We have our midpoint between our KL divergence between P and the midpoint distribution, and Q and the midpoint distribution. Now, this M, if we look at what M is, it's the arithmetic mean of the two distributions. And so what we did is we changed the mean, substituting the family of Shishini means, the geometric mean, harmonic mean, and there are several other means that you can insert. And this gives us a new type of Jensen-Shannon divergence, a so-called dilated Jensen-Shannon divergence. It takes the range of the Jensen-Shannon divergence and it changes it from the closed interval between 0 and 1 and changes it to the closed interval between 0 and infinity. It basically stretches out your Jensen-Shannon divergence so that if you have subtle differences between distribution P and Q, the Jensen-Shannon divergence will amplify that so that subtle differences are more discriminable. You can tease them apart better. And so this is work that I did directing the work of my graduate students. He's now a research scientist at a government research lab. So this is CJSD, Shishini Jensen-Shannon divergence, where we substitute for this mean different family of means from the Shishini means, and you can use other families of means in this framework. And it gives you different dilations. It gives you very desirable properties with the resulting ability to tease apart different types of differences between your distributions P and Q. And so this other one that we'll talk about, this is another type of divergence. This is called f-entropy, or sometimes Bregman divergence. And so let's say you have an arbitrary function. Now we're not just talking about probabilities anymore, we're talking about functions. And these functions have a particular property. They're convex. They also have a domain, the input to this function, that is a convex set. And the derivative of this function has to be monotonically increasing. That's required. All special functions f that have this property can participate in this type of entropy. And so here we have this f-entropy between distribution producing values w and v is just f of w minus f of v, right? That's just the rate of change of f between two different values, minus the difference between w and v times the gradient of our function f. And so if we look at this on the graph, here we have f, that's our curve, and we have point v, and we have w. W minus v is this interval, w minus v is that distance between w and v. And so here we evaluate f on v, and we evaluate f on w. And so if we look at f at w and f at v, and we subtract f of v from f of w, that's this distance. It's the increase in our function f going from its evaluation of v and w. And now what we're doing, we're comparing this rate of increase in f, our function, and we're comparing that to the linear projection at the tangent of f at v. So here's our tangent line. That's the slope, local slope at point f of v for that function. And if we were to project forward along that tangent, a linear projection going forward some distance W minus V, that difference between W and V, well, what is that? That's in this direction along that tangent at, F that's incident where F of V is evaluated, F's value at V. And so if we project that forward, that particular point here, that's going to be F of V plus this projection forward. And so we take the gradient of F at V and we project forward this delta, and we're going to compare this new version of the function against this increase in F. And we're going to compare the two together. And that difference here is this distance, and that's going to be called our f-entropy. And what the f-entropy does, it says how different is the rate of change for the function from the linear projection of that function sloping at point. All right. And so that's called f-entropy. And the beauty of this, if you think about what entropy means at the outset, we said it looks at the number of alternatives that a function can take on. And so in this case, we're generalizing that number of alternatives to how the function changes. Because when it changes, going from f of v to f of w, it's going through a set of values in between. So it says as you go a certain distance, w minus v away, how does that compare to the slope projecting along that constant rate of change at f of v? Okay, and this is called f-entropy. Sometimes it's called Bregman divergence. But this f-entropy is more general, and it's a nice framework that you can define an entropy on a broader class of functions beyond just probabilities. All right, so let's take a look at decision trees now that we've gone over all sorts of methods for looking at information. And so a decision tree is a classifier generation method, classifier induction, and it's for learning the target function that assigns labels y to feature vectors, input instances, x. And so the one requirement is that our label set is discrete. That means our labels have some finite cardinality. All right. So a family of decision tree algorithms includes ID3, and it includes also the other algorithm, C4.5, which is an improvement on ID3. Now, you might be wondering why we're discussing decision trees. Well, their benefit is ultimately because they're interpretable. Once you learn a certain prediction rule, you can then examine that classifier and follow it and look at the decisions that one needs to make. And this is immensely useful for things like medical diagnosis, for credit risk, etc. So now if someone says, well, why was I denied for this loan? Well, the tree said your income was lower than a certain amount, your years in residence was lower than a certain amount, etc. And so interpretable models are really, really good because you can now look at and use those model decisions as the basis of real decision making, and it's explainable. So you start out with a number of in-sample points, label instance pairs. So here are our feature vectors. These are our features. And we have our labels. And we have n many of them, a data set of size big X. And so our label set for each one of the labels we have are drawn from a set, and it can be from k many different labels. We have label L1, L2, L3, up through and including LK. In the binary classification sense, we only have a label set of cardinality 2, L1 and L2. And you could call one the plus one label, one the minus one label, cat, dog, or what have you. So each one of these labels is drawn from a finite set of size k. All right. And so with a decision tree, how does this work? You start these instances down a tree structure. And so you take your label instance pairs and you set them down a bunch of nodes. And then eventually these nodes, each one tests some attribute within your feature set for the feature vector, for your data. And then you go, based on that test, pursue a subtree rooted in one of the children of that node. And so each one of these nodes in the tree is a type of test based on feature values. And then eventually you walk down the tree examining different features until it comes to rest this instance at one of the leaf nodes in the tree structure. And so this interpretability comes from the set of test nodes, because these test nodes ask a question about the features corresponding to the feature vectors. And so eventually you arrive at a leaf node, and this leaf node will then provide the classification for that input instance. Each node corresponds to a test of some attribute. And so for these tests, we're going to begin with our whole data set. Each node corresponds to a test of some attribute. And so we're going to begin with our entire data set in the form of a design matrix. So in this case, we have big X, and big X is a row matrix. So each row in our design matrix is going to be one of the feature vectors for each data point. And so here we have x1 in d dimensions, x2 in d dimensions, up to and including xn in d dimensions. And so each one of these vectors has some number of features, the same dimensionality, so d many features. And so each attribute in this design matrix is going to be a single column. We're going to have the first feature, the second feature, the third feature, including up to and including the d feature for d-dimensional representation. And so we have, for each attribute or each feature or variable, we can use feature as a synonym for attribute. You're going to have an instantiation of its values. And so here we have a single column here, and we're going to have I represents the instance, and that instance goes from the first instance to the nth instance, and then J is going to represent the feature. And so this would be J is equal to 1, J equals 1, up through J is equal to D for D-dimensional features. And so Xij is going to take on values. X1J, that's going to be for the first instance feature J, second instance feature J, the nth instance the J feature. And so for all of the attributes in D dimensions, we're going to have n occurrences of a value. And this is going to be the domain of that random variable. All right. So in order to test an attribute, what you're doing is you're evaluating these values. And you're going to ask the question, for a given value, is that particular attribute, is it greater than or less than equal to a particular value, we'll call that A, drawn from the set of values for the domain of that particular attribute. And so here's one question. Is it greater than A or less than equal to A, drawn from the set of all the different values your attribute can take on over n many instances? And so that's going to be a yes/no question. And when you perform classification, then each one of those tests that corresponds to that less than, greater than, equal to for each node, you're going to take a new input feature vector, you're going to calculate its features, and then you're going to start it at the root node, evaluate the test. Now, when you evaluate this test, you're going to then pursue a branch emanating from that node for which the test is true. Now, if it's numerical, is the test true? If it's categorical, is it that particular value, like low, medium, and high, like pineapple, dog, or apples, for example. So then you keep repeating this process at the next node you encounter once you pursue a branch based on the outcome of that test at a particular node. And so you're going to repeat this again and again and again until eventually that new input instance is going to reach a leaf node, and it keeps repeating itself. So here's an example. We have a 4-dimensional feature vector, and we're going to have 4 different attributes, one for each feature. One is called outlook, and that's going to be the outlook of the weather, whether it's sunny, overcast, or rainy, so that's categorical. And then we're going to have the temperature. The temperature is either going to be hot or it's going to be cold. The humidity can either be high or it can be normal. And the wind is going to be strong or it's going to be weak. And so if we were to input a particular feature vector, a new vector, let's imagine outlook was sunny, the temperature was hot, the humidity was high, and the wind was strong. So we take that vector, sunny, hot, high, and strong, and we now input it through the first test node. And so this test node says, okay, what is the outlook? And it can be sunny, overcast, or rain. Oh, it's sunny. So now we pursue that left-hand branch for sunny. So then we look at the humidity. Humidity, let's see. Humidity, is it high or is it normal? It's high. Okay, so now we're going to pursue that left branch. And we reach this leaf node, and it says, no, we should not play tennis. And so this particular decision tree, it will determine, based on all of these factors for outlook, temperature, humidity, and wind, whether or not, yes or no, should we go out and play tennis. And so this decision then for the outcome categorization for this feature vector, this new one, is no. We should not go out and play tennis. It's predicted that the label for play or not play is no label. Should not play tennis. And so the explanation is, well, the outlook was sunny and it's high humidity, so we shouldn't play. And so now you can have an explanation about why this particular decision tree output the no response instead of a yes response. Okay. And so a decision tree is nothing more than a conjunction and disjunction of tests on attributes. So these are our conjunctions, the anding, and we have a disjunction of these conjunctions, the oring together of these different disjunctions. All right. And so the types of problems well suited for decision trees are those that are described using attribute value pairs, where you have a fixed set of attributes, and they're either continuous or real valued, works for that too. It's better, easier for categorical, but with continuous real values, you can just quantize those real values into levels that are descriptive enough for the particular problem at hand that you're considering. You can have disjunctions where you have discrete set of outputs and the training data possibly has errors. Decision trees are good for that. And also decision trees are good for problems where the training data, the in-sample points, may have some missing attributes. So let's take a look at how you build these decision trees, how you select which particular tests you're going to arrange in order to build your classifier. And so the question then, how do you create the tree? It's essentially searching for the best tree, but what does best even mean? So when you're searching for a tree, well, you're taking your data, historical data, and you want to know, how do you organize these tests, these nodes of the tree? And so you're going to use a greedy search to do this, but what does this best mean? It's trying to optimize or maximize or minimize on something. And so to encode this notion and mechanize this notion of best tree, you need a statistical test for best. And so the best attribute then is one that is good or useful for arranging all of the patterns, all of your input data, your historical data, into groups. And so you're going to start out with your data set, vector x1, vector x2, and so forth, up to including vector xn. And so you're going to end up separating your patterns, your vectors, into groups. And you want to choose the values as the basis for this test that you currently have for each attribute. So you're only going to consider values of the different variables or features that exist in your data set, nothing else. And so when you do this then, a descendant or child node is created for each value of the attribute. So you're going to be testing each value that these variables can take on, and then you're going to sort the inputs or group them based on the outcome of the test over the values of the different attributes. And so what's useful to use is this idea of information gain. And what the measurement of information gain is information theoretic, and it tells you how well an attribute separates your examples into groups such that these groups are as homogeneous as possible in the ground truth label. And so let's say if you had x1 and you had x2 dot 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 x big N, and let's say you had these features and you could put them into groups. Maybe these two are in one group, these two are another group, these two are another group. And when you look at their class label, yi, well, these just happen to be all the dog images. These just happen to be all the pineapple images, and these just happen to be all the apple images. Now, if it's perfect that only the dogs are in this group, only the pineapples are in this group, only the apples in this group, great. But you might have maybe a single instance of a pineapple among this group. But what this information gain tells you is how well a particular test on the attribute will result in the partitioning of your data into groups associated with more homogeneous ground truth class labels. And so if you have a high entropy group, that means there are more possible values or outcomes. That means you have a larger number of different ground truth class labels associated with the inputs in a group. If you have low entropy, that means you have fewer outcomes. So that means you're more homogeneous. This means homogeneous in the class label, resulting in the groups you get when you separate your data points as a result of running one of these tests. And so you're given your label instance pairs for your data set, all n, many of them. And let's assume the case where you have a binary class label, the +1 examples and the -1 examples. And let's assume Ti is the probability of the ICE class. So you have a probability of the plus label and a probability of the minus label. So the entropy of your data set is then the weighted sum, the expected log probability. So we have minus probability of the plus examples, log probability of plus examples, minus probability of minus negative examples, log times log of the negative examples. So this is just your sum for all instantiations of Ti log Ti, the negative expected log probability for each one of the labels. And that's for the resulting groupings as a result of these tests for attribute values less than or greater than equal to for each one of the attribute values observed for the attributes in the vectors for your data set. All right. And so entropy measures this idea of diversity or impurity. And when you talk about this diversity or impurity, you're looking at the level of differences that you have. And so in ID3, information gain talks about this reduction in entropy. As a result of running these tests for the nodes in the decision tree, how's entropy reduced? Gaining information allows you to reduce or sort the groups of inputs. There's less plurality in the number of class labels for the resulting subgroups. And so let's take a look at our expression for information gain. So information gain for set S and attribute A is this entropy for the original set minus this sum for each one of the values of that attribute A. You're going to take the probability, so the proportion between the size of the subset you get that have a particular value V for that particular attribute divided by the size of the original set. So this is going to be a probability. So that's my probability of having a value of V for attribute A. And then you're going to use that probability to compute a weighted sum, the entropy of that subgroup that has a particular value V for that attribute. And so the original entropy for your group, you're going to subtract the expected entropy for each one of the subsets induced by considering only that subset that have a certain value for an attribute. And so val is a set of values for attribute A. SV is the subset of your original group of instances S, with attributes have a particular value V. And then SV is all of those data points from the original original set of data points such that that attribute has the particular value. All right, and so this is the entropy before you sort the groups or partition the subgroups, and this is the expected entropy for each one of the subgroups. And so you're subtracting off the expected entropy across the subgroups from the original entropy before you partitioned into subgroups. All right, and so this information gain describes the information about the target function, about that class label, given a value of some of the attributes. And this gain is the number of bits that you save when you encode a value in the face of certain information from your attribute. And it's that reduction in the number of bits that you need. And so ID3, iterative dichotomizer 3, it uses this information gain to select attributes for your test nodes. And so you search the hypothesis space by considering the tests that will produce the largest information gain, the largest reduction in the number of bits needed to encode when you split, resulting from those splits of the original data set into smaller subsets. Okay, so ID3 searches your hypothesis set for that best hypothesis that coincides with your target function. Coincidence with the target function means you group them together, your instances, into homogeneous class labels. And so there's an inherent bias that exists with ID3. It's going to favor attributes that have a large number of different values versus those that have a smaller number of values. And so if you look at the expression for information gain, you notice here we have this probability and we have the entropy of that subgroup, entropy relative to the class label. Now, if you have a larger number of values, that means you're going to have a smaller number of instances that's going to have that value. So let's say if you had 100 instances and a particular attribute had 4 different values and another attribute had 20 values. The attribute that has 20 different values, well, those 20 values are observed in the data set. So that means each one of the partitions based on those 20 values with a larger number of values for an attribute, those are going to be smaller groups. And if they're smaller groups, this probability is going to be smaller, and this entropy is going to be larger, right? This entropy is going to be smaller. And so this reduction rather than gain is going to be a more dramatic information gain because you're going to go from a smaller number of alternatives, less entropy, and you're going to take something that's smaller and you're going to subtract it from the original entropy, and that's going to result in a larger information gain. And so it's going to therefore favor those attributes or tests involving those attributes if the attribute has a lot of different values. And so we need to account for that because essentially it's going to bias our splits into more numerous valued attributes, and we don't want to do that. And so Ross Quinlan came along and he implemented this thing called the gain ratio, and he added a penalty term that effectively normalizes this information gain, accounting for what I'll call the bushiness, right? How many different values or bushy the split is if you're considering a node, right, as a test, and each one of these edges from that node represents a different value of the attribute. So if you have increased bushiness, you want to account for that. So here is information gain, and this information gain, as before, it's the original entropy minus the expected entropy across all of the different values inducing splits. And then we have this other quantity called the split information. The split information for a particular set of instances and attribute is this expected log probability. And so here we have SI is the subset induced by partitioning on a certain attribute value, and that's relative size of the attribute relative the size of the subset relative to the size of the original set before partitioning times the log of that probability. right? So you take the split information, and the split information is a measurement of the bushiness. It's sort of the information or the entropy in the bushiness, or the number of alternatives you have resulting from splits induced by the larger number or the number of alternatives you have for a variable's value in the data set. And so the split information, Quinlan came along and he said, okay, I'm going to pose this thing called gain ratio. And gain ratio takes my information gain, the reduction in the number of bits needed, and I'm going to normalize that by the bushiness. So essentially, you're partitioning or you're spreading that gain ratio and saying, how much savings did I gain in the representation? And now I'm equally attributing to that savings to the bushiness. So if you have a large gain but a high bushiness, it's going to count for that high bushiness than if you had a large gain and a small bushiness. And this gain ratio is the negative of information gain divided by the split information, which is this bushiness, the encoding of the bits due to the bushiness versus the reduction in the number of bits needed due to this partitioning. And so this gain ratio discourages the selection of splits that result in groupings that are closer to being a uniform distribution. Because if you have a large uniform distribution, you're going to have a small gain ratio. So it encourages smaller split information or smaller distribution over the number of variables. And so this penalty makes it more fair, really representing the reason why you had a reduction in the information representation. It's more truly due to that reduction and not because of the bushiness of that test node in the tree. Okay, so with that, that's all I had for today. And as usual, please stay healthy, stay safe. Please make sure you're keeping up with the reading. And I'll see you all on Tuesday.